So this is part 2, and if you look at your schedule, most of the discussions are going to be organized as sort of 45-minute discussions with a 15-minute break and a 45-minute discussion. One of the things I encourage you to do is to participate in the discussion. It actually helps a lot in terms of your own understanding and self-assessment. One of the problems of all disciplines, even ours, is we divide up into tribes or clans or domains. And so at the Science Mission Directorate at NASA, you can think of heliophysics as being one of the tribes, and there's of course astrophysics and planetary physics and earth science, right? So they're competing for resources. But even within heliophysics, we have our own tribes, and if you look at AGU, we have our SA, SH, SM, so the solar heliosphere, magnetosphere, and ionosphere, thermosphere. If you look at NSF, the geospace sciences is divided up between those same tribes, so you either go to SHINE or GEM or CEDAR, right? Different topical domains. And so if you're going to be a heliophysicist, you're going to be talking across these domains, and we often will use different terms for essentially the same thing. And so again, put on your similarity and difference hat. Why do they call it something different? And it could be it's completely historical. It has no physical difference. And once you realize that, then all the jargon won't fly by. So we're going to talk about processes, and the goal of this lecture is to talk about scales. And as I mentioned, this is what you should have on the tip of your tongue. It's sort of part of your 30-second elevator pitch. And if you're talking to other physicists, you can know what type of physicist they are by what type of scale they keep in their back of their head. If they're a megaparsec person, they're a cosmologist. And if they're a nanometer person, they're probably condensed matter, right? We all have our scales. And some of us are still CGS, some of us are SI, but that's who we are. And it's who we are because that's the problem. And so when you think of the equations, that curl B or the grad P or whatever, the left-hand side is a d by dt, so that's a time scale. And on the right-hand side, you have these gradients and curls, which are length scales. How much does B change over a distance? How much does pressure change? So right off the bat, by just looking at your problem, I can say, oh, the gradient is really small over what I'm interested in. I'm going to neglect this term or whatnot, right? So that's what we're doing. We're trying to simplify our complete equations. One of the difficulties and the reason why we as a community are investing a lot of money on magnetospheric multiscale is that reconnection is at the heart of almost all of the physics problems of our discipline, but it's been a really tough problem to crack. And it's because it's a cross-scale problem. Reconnection physics is at the electron scale. So at the smallest scales you can think of a plasma, sort of electrogyroradii or something. But of course, the consequences of magnetic reconnection has global impact. We talk about geomagnetic storms have a global impact. It influences the ionosphere, the inner magnetosphere, the magnetotail, right? But it's this microphysics that's doing it. But of course, the global configuration of the magnetosphere influences the rate of reconnection, and if reconnection happens. So it's truly cross-scale. You have influencing going both ways. And so that's why it's tough, is that we have to make measurements over a huge range of scales. So think about your physics, what scales they are on, and then think about, again, those boxes that are outside your domain, which ones come in, which arrows go out, and what are the scales? Is it really a global, I'm a thermosphere person, so now I have to worry about this boundary condition of everything out in space? And so it could be from cosmic rays to auroral precipitation. So now I'm looking at spatial scales, or is it something on a substorm, a storm, a solar cycle, right? So those are the types of questions you should be asking. And to make a name for yourself, you know, improve an instrument by a factor of 10. That's one guarantee. But the other one is to ask a question that somebody hasn't asked before in terms of this cross-scale coupling. And a lot of times we just think about it quickly, oh, the time scales are much too long to be important for my problem. But think about, is there a way that that long-term or large-scale phenomena has intermediaries? So there are other physics that goes on that then influences your problem, and you can start answering some of the long problems. Okay, we're just going to do a test to see how well you did. So this is a cavity, and we have our Voyagers popping out into the heliosheath and through the termination shock, and hopefully exploring interstellar medium. And so this is an example of a cavity. This is one of my favorite places in the universe, the Orion Nebula. And what's cool is you can calculate how much grain alcohol is in this nebula. And it's like 10 to the 18 fifths of pure grain alcohol. So they are living it up. Of course, it's spread out over many light years. But this is a picture from the Hubble Space Telescope of essentially our heliopause, right? We have a relative motion with the interstellar medium, and we have a blunt side and out. We now know from IBEX that we might not be going supersonically relative to the interstellar medium, so we might not have a shock outside the heliopause. It might just be like a bow wave. But you can find examples around other astrospheres. You're going to hear a lot about the different magnetospheres just in our neighborhood, in our solar system, and the different scales of Mercury and the Earth and Jupiter and Saturn, and how all of them would fit inside each other. As I mentioned, these nesting dolls, but of course you could have the moons, and so JUICE. One of the cool things about that is looking at these moons that have their own intrinsic magnetic field. They're inside a magnetosphere that's being buffeted by the solar wind. So how are they controlled? So here's your question. What is this? It's an artist's rendition from NASA. An astrosphere, a heliosphere, a planetary magnetosphere, a satellite magnetosphere. We have some boundary, some field lines, something in the middle. So it looks like a bow shock, so a planetary magnetosphere. I don't know, does Ganymede have a shock in front? No, so it's all subsonic alphanic wings, I guess, now if I'm remembering. Yeah, so actually I don't know what it is. But you could have, I could have labeled it anything, and it would have worked, right? So there's similarities in structure of a plasma universe. And you could take a textbook looking at bow shocks and just move it into an astrophysical to a planetary to a space physics domain. It's a very similar physics. Of course, the local environment could have dramatic differences in the detail of the structure. It's still a pause, it's still a shock wave, but it could be very different in terms of Mach number, in terms of orientations, all types of things that can give rise to very different effects. And so that's what makes it interesting. Okay. So introduce yourself to your neighbors again. And it could be a group of 4, group of 3, whatever. See if you can answer these 3 questions. What determines the structure of a magnetosphere? So if I was just going to ask you on a qualifying exam, tell me what parameters determine the structure of a magnetosphere. What do you need to measure or write down? What determines its dynamics, its time scales, what it does? See if you can write it down or discuss it. And when you think about plasma physics, we're following three things: mass, momentum, and energy. And so if you look at all of the NASA roadmap and all of the missions, there's going to be somewhere we're trying to look at how energy flows through the system, how mass flows through the system, how momentum changes it. So how does it go through these coupled systems from the solar wind into the magnetosphere? I'm going to give you 2 minutes on this one, so go at it. Okay, everyone. Anybody want to volunteer somebody in your group to tell me the answer?
Volunteer somebody else in your group?
That's right.
Yeah, okay.
You can point. What determines the structure of a magnetosphere? This is the easy one. Okay. 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 So external flows and the strength of the.
You're talking about, for example, diamonds and also the magnetosphere of the giant planets.
Okay. Internal, external. But what do I need fields? Or am I actually needing to balance?
Planet's fields would be closed inside the magnetosphere, and outside the magnetosphere you would have either interplanetary magnetisfields,
Okay. So
you came up with like the overall structure would be defined by the Dirac pressure
pressure.
and the magnetic field of the source planet.
So how does a magnetic field hold off ram pressure? How does it? What's that? So a balance of what? So magnetic pressure, okay. So dynamic pressure, so pressure I should have the same units on right and left hand side of the equation, okay. So one of my first questions in my qualifying exam was from Al Marsher, who some of us know. What determines the rate of a dripping faucet? And I'm a space plasma physicist. But can you think about what are the physics that determines structure and dynamics? You know, you can think about flow rate and viscosity and the strength of gravity, right? Like, and that was his only question. Once I answered that, he go, okay, I'm done. So that's what you're looking for. Can you distill a problem down to some of the fundamental physics? What are the forces that are important? So if you're going to design a mission to go to another planet and you have no idea where the boundaries are, you might argue that I really need an upwind solar wind monitor. Otherwise, I wouldn't be able to get the global structure, right? So you have to go through that. So a little bit tougher. Okay, I know what the structure is. What determines the dynamics? Anybody want to volunteer? Either a question or an answer? Plasma beta, how does that determine dynamics?
Plasma beta is just the ratio of gas pressure to magnetic pressure. You have gas pressure dominates, plasma flows in the plasma. Plasma flows you at rate of need this magnetic fields. Magnetic pressure is dominating magnetic pressure rate controlling plasma.
Okay, so a plasma beta tells you the importance of the two different terms, so that could tell me the process that's important for the dynamics. Right, so if I have a high beta, low beta, it can tell me. What actually determines the DT? Okay, solar stellar cycle. But do I need to worry about what phase of the solar cycle I'm in when I'm dealing with substorms? So variation of the solar parameter, so I can have difference in IMF and solar wind. Yeah. So what would be a scale? Okay, so I have the size. How about a time scale? What would be a time scale? Sure. So obviously, if you look at the momentum equation, we have a dv dt. So a velocity over a time gives us a scale, right? So if I have some alphanic velocity or sound speed, and I tell you the scale, you can tell me, you know, that's much too big, I can't communicate information or whatever, right? So those are the types of things we're looking at. But what is a time scale of importance to a magnetosphere? No one right answer.
Minutes to hours.
So minutes to hours, what determines minutes to hours? So solar activity, so the time scale of a flare, time scale of a coronal mass ejection, time scale of a CIR crossing the magnetosphere, right? So there's tons of scales. Jan?
There is the totally internal time scale for instability after energy loading. It may have nothing at all to do with your solar wind.
Right. So we have the timescales of the drivers, but we could also have some internal timescales, and they could be all over the place. They could be geodynamo timescales, and we were thinking about, you know, what happens when the dipole field goes down? How would that change aurora? And we might get more interest if we had aurora everywhere, if we had many auroral ovals all over the octopoles of the Earth. But so all of these are trick questions in the sense that there's tons of scales. And when you talk about structure, do I mean 10 RE upstream, or the flaring angle, or the length of the magnetotail, or the width of the plasma sheet, or the ring current? From what L to what L, right? So we have all of the different time and length scales that people in our community are examining. But ultimately what we're looking for is this flow of mass, momentum, and energy. Anybody want to take a crack at how do we get mass through the magnetosphere? So, let's say solar wind plasma into the magnetosphere. We have magnetic reconnection in the magnetotail that can energize particles towards the Earth. John?
It's probably a small effect, but there's some things that come in through the cusp, and most of those will probably end up in the atmosphere and contribute to aurora, but a few will probably get scattered into the inner magnetosphere on the way down.
Sure. So that was one of the big open questions a while ago, is how do you get, if the magnetosphere is a cavity and magnetic flux tubes are mutually repulsive rubber bands, how do I get an IMF flux tube to deposit solar wind plasma into the magnetosphere? And so that was Dungey's insight, is that I can have this topology change where I actually can connect two different field lines and make two different. So I can have a solar wind field line and a closed magnetospheric field line. Closed meaning it has connections to both ends of the Earth. And I can make two new field lines, open field lines that have one end in the poles and one end in the solar wind. And so I can dump mass, momentum, and energy into the system through this process of reconnection. So for essentially my lifetime, not that I have been thinking about reconnection since the mid-60s, but people have been trying to figure out why this happens, what determines the rate, the location. Is it steady? Is it bursty? Are there internal instabilities? Why is there an imbalance between the day side and the night side? We don't have the day side magnetosphere get completely eroded down to the atmosphere. There has to be some return flux. What determines that flow? What are the consequences of that on the atmosphere and the thermosphere and the ionosphere? What energizes the radiation belts of Van Allen? When we measure the geomagnetic storm, that DST, where does that particles come from? What's the connection, right? So all of these are looking at these timescales, but reconnection is the name. And Nick and I have had an argument that he doesn't realize yet.
Oh, no, I figured it out.
Oh, okay. A referee of a paper. What's reconnection? If I asked you just to write down a simple elevator pitch, you're going to a high school and you're working on MMS. What's the definition of reconnection? I study reconnection. What is reconnection? What would you write down? And what's interesting is that I think we've agreed that if you ask 50 space physicists, you'd probably get some subset of different answers of what it is. And I like to think of it as two things. It's a change in topology. I break these field lines. I can cut these rubber bands, these flux tubes, so I can get an intermixing of plasma and a change in topology. I can go from an IMF field line to an open field line, or a closed field line to an open field line and back. But I also have this very rapid diffusion of the magnetic field. The magnetic field goes away. So you can sort of think about it as a vector field. If I have a 10 nanotesla field going up and a 10 nanotesla field bringing down, and I bring them together in a reconnection process, just in vector algebra, 10 nanotesla up, 10 nanotesla going down, what's the total field at that null? 0. So a magnetic field is a force field. It has an energy density, right? B squared over 2 mu naught. Where did that energy go? Conservation of energy says I can't create or destroy energy, so it has to go somewhere. So where did it go? It goes into heat, plasma, acceleration, right? Generating electric, all types of things, right? So that's my definition, is two things: topology change and this conversion of magnetic energy into plasma, kinetic, and thermal energy. The debate is, though, reconnection has a lot of different consequences. Other things happen in the system that we often will call reconnection. Yep.
Now, what I understand is something like changing of topology, but now plasma
So what happens, so all of these we talk about here, ions and electrons are obviously connected, and in this ideal MHD world, they don't exist. So right off the bat, I have to switch my framework when I'm thinking about reconnection. Ideal MHD does not explain reconnection, because I'm thinking about on time scales and length scales where things are happening much faster and over shorter distance than my typical ion scales. So MHD is slow, large scales. And so suddenly I'm in a domain of short, small scales. So if I keep my reconnection hat on, or my MHD hat on, it's really hard to explain any of this, because I'm not talking about particles. I'm talking about flux tubes disconnecting and breaking and generating electric fields, but what's carrying the electric fields and whatnot. So this is part of this cross-scale issue. I generally think of the global structure I, and colleagues in the MHD, ideal MHD world, think of the global structure in a fluid frame. But in this region, I am no longer in a fluid regime. The scales are much too short and small. So now I have to go into a kinetic regime. And I have to think about ions and electrons separately because they have their own length scales. I have an ion gyroradii that has a much larger length scale than electrons. And so I can imagine at some scale my ions decouple. So my gradient in my field becomes small enough that as I'm trying to go around a field, I'm going to very different fields. And so I'm no longer tied to that field line or in that flux tube. But the electrons are much smaller, so they still see a field. So now I have different ion and electron physics. Right? And then I can imagine I can go down to a smaller scale where suddenly my electrons no longer see a uniform field in a single gyration. So that's what's sort of meant by this cross-coupling, and where you need to be conversant and understand when the model that you are taking into the problem no longer works. You get into trouble. So we talked about the self-similarity of magnetospheres and all these scaling parameters, and we just mentioned a few scales. Instead of telling your neighbor, see if you can write down 5 plasma scales. It could be a time scale or a length scale. Just, you don't have to write the full equation. Just, I talked about the ion and electron gyro radii. You can use those, so 3. See if you can write down 3. Go ahead, you have 30 seconds. Length or time. Right. So you can cheat. Gyro radii and okay, hopefully everybody has a few. Just throw one out. Plasma frequency. So what does plasma frequency depend on? Number density. Anything else? And ion mass. Anything else? And constants. So it tells you something about the composition and the density of the plasma. Throw out another one. Gyro frequency. So you have a gyro radii, you have a corresponding time scale. What does that depend on? Charge, magnetic field, mass. Anything else? Throw out another. So, which one? So how is that a time scale? So a velocity of what? So energy. Okay. Yep. Does velocity have a scale? Can you think of a typical scale? So you can talk about so you can think of about sound speed, Alfvén speed, right? I mean, so those have scales, and over your domain, they would give you a sense of timescales. So we've had B, M, N. Can anybody think of another scale that deals with something other than B, M, N? What's that? Temperature, what is temperature? And, okay, and so you can think of that as a scale in terms of an acoustic sound speed, I guess. And so what does that depend on? What is the thermal speed? What does temperature depend on? So if I was going to, what's the sound speed? Calculate the sound speed of the solar wind. In terms of your parameters, B, M, N, what's E? So electric field, does electric field determine the sound speed? Right? So can anybody think of any other parameter that you need to measure if you want to characterize a plasma? So what does Debye length depend on? So density, temperature, and your charge, right? Okay, so we have Q, M, B, N. Anything else? So if I'm going to design a NASA mission to study the corona, solar orbiter, MAVEN, what else do I need to measure? I need magnetic fields, composition, density. Do I have it all? That's all I need? So if I look at so electric fields. So if I start thinking about my Maxwell's equations, so I want to, in terms of plasma parameters that set up scale sizes, right? Density, composition. Okay, so N or rho, we'll get that. And so that determines all the scale sizes, right? Tell me what it's made out of. Is it ion, electrons, oxygen, hydrogen, how dense it is, and the strength of the magnetic field. And that determines almost all of my scales, my Alfvén velocities, my temperature gives me my thermal Debye length and all that. So there's not a lot of parameters. So you should go through, look at wind, ACE, stereo, Janet's impact experiment. What are all of the in situ measurements? And many of them measure the same thing. Why would you want to measure the same thing on a single spacecraft? You're resource constrained. Why don't I just measure one thing? So double check. So go to JGR Space Physics, look at any data from any mission and find an example of an error bar. And I would love to see it. Notoriously, all of our measurements are absolutely accurate and precise. We're one of the only fields of physics that doesn't do that. The only time you see an error bar is if you bend things and you'll show quartiles or something like that, or medians. But usually, for some of them, like magnetometers, the error bar might be the thickness of the line. But a lot of things have a lot of uncertainties. And if you compare wind versus ACE, depending on the plasma regime, you can get very different things because the type of instrument is very different. The thing to think about, some instruments give you a lot of things. So a plasma wave instrument can give you an upper hybrid or a plasma frequency plus things about the wave environment, right? So when you're picking your instruments, if you can get a twofer, you might as well do that. But you might be interested not only in N, you might want to be interested in the plasma distribution function. How many particles are going at a certain velocity, so then I would need a different instrument. So when you look at MMS, it's essentially trying to measure all of those timescales, all of those plasma parameters. So it has magnetic fields and plasma instruments. But the other thing you have to worry about is if I need a distribution function or an N, at what time scale do I need to make a measurement? What is the cadence of my measurement? And I better have more measurements in time than the fluctuation of what I'm trying to measure. And that's been one of the difficulties of reconnection, is that we've been flying spacecraft through the magnetosphere and solar wind for a long time, but it's really hard to make enough measurements in this region called the diffusion region, where the magnetic field rapidly decays away. But this is another nesting picture, just like the dolls. Here's the global configuration of the dayside magnetosphere. We're looking at magnetic reconnection on that dayside. If I zoom in to an ion scale on the order of hundreds of kilometers, I can see this very thin current sheet where the fields are in opposite direction around it. And then as I go into the tens of kilometer scale, this is the size of the diffusion region where those electrons enter in the region. So here are some of the scales. Again, we have M, energy or velocity, charge, magnetic field, and they determine all types of things. We have composition, MI again. So we have all these different scales, and we have electron and ion. We have oxygen and helium and hydrogen, right? So all of them have their own scales. We're often dealing in a collision-less plasma, so we can have all different types of distributions coexisting in the same place. So we can have a radiation belt and a plasmasphere, MEV electrons and sub-EV ions, and they just move right through each other. So there's a whole bunch of Debye, skin depth, bounce, drift, mean free paths. And so one of the questions that you'll be asked when you try to solve analytically or numerically or design an experiment, which timescale is relevant for your problem? What timescale tells me about the physics? So all of these usually tell you about a term in the momentum equation or the energy equation, or in your source and loss terms in your continuity equation. It tells you about one of those. And so if your problem is much longer than it, so I can neglect this. So you just start throwing things out. A bounce period might be long compared to my reconnection physics, so I don't have to worry about those. So as we just mentioned, this is how I think of reconnection. Conversion of magnetic energy into plasma kinetic and thermal energy, and the change in field topology. And so the consequences of this are vast. It can explain a lot of things. What's a flare? How do I get a coronal mass ejection to erupt? How do I get a substorm? How do I energize particles to make seed populations for waves to energize them in the inner radiation belts? How do I energize particles to precipitate to make aurora? I need to get energy from somewhere. And so generally what we're going to be doing is we're going to build an X-ray instrument to measure, I wonder what's happening in the magnetopause of Jupiter. And then I said, what process can I do to make X-rays? What temperature thermal plasma or what energy Bremsstrahlung or whatever do I need to make X-rays? And so I see them, so then I have to figure out what the physics are and where do I get that energy? So then we can do energy budgets. Is there enough energy in the magnetic field? Is there enough energy in this time scale? And you can say, yes, there's a lot of energy here, or no, and you can figure it out. This is the, yes, please.
It's not changing topology, it's changing connectivity. Because in fact, if there were such a thing as a steady wave and a steady Dungey cycle, topology will always be the same. It's just be migrating the field connectivity through those domains.
Okay. So one of the difference you can think of is what scale, time scale are you thinking in that system, if you're thinking of an entire cycle or just of an event. So if I'm just following an individual flux tube, I can think of I was connected both ends to the sun, and now I have one end connected to the sun and one to the earth. But of course, as the cycle continues, then I'll go back, and so the net topology change. And Janet's written papers on looking at the sort of total flux in the heliosphere. When you look at these reconnections and coronal mass ejections, what they contribute as flux removes. But this is the Dungey cycle. It's essentially this southward IMF connects at a neutral point here on this two-dimensional drawing. And Nancy Crooker and Janet Lumen had drawn a lot of pictures of where this happens in different configurations on the day side in three-dimensional topologies. But in just thinking of it in 2D, I go from an IMF field line and a closed field line to a new one that's connected to the north and to the south. It gets drifted back. I can reconnect it and have this convection come back forward. So this complete cycle has the solar wind flux tube reconnecting with the magnetospheric flux tube, magnetospheric open flux tubes reconnect, forming closed flux tubes, and it continues on. So we talked about timescales. We talked about different individual plasma parameters and all the ways we can mix them together to get some feel for the scales of what's going on. So I can put N and M and B and V in different organizations, and I get some characteristic time or length scale. But really what we're doing is we're accountants. We're trying to keep track of energy, because we know that energy is what makes things go. Right? It provides the ability to do work, to twist flux tubes, to have the reconnection. And the energy in a magnetic field is that source of a large amount of energy in all of the systems we've talked about before. When Hale first did a Zeeman camera on the sun to measure the sunspot magnetic field, we now could then calculate, is that enough energy to explain a flare? Why, it is. So maybe we can now do an energy balance. So we know that, as we saw in that movie, looking at the visible, we had dark sunspots, and as we looked in the extreme ultraviolet and the X-rays, we saw those spots. How did we heat that plasma? How did we make the corona so hot? How did we make those active regions? What describes a flare? How do we get the coronal mass ejection? How do we get the geomagnetic storm and substorm? We take a look at trying to convert this energy. So of course, scale is important, and all of these phenomena have really short time scales. Anybody know a characteristic time scale of a flare, a solar flare? 10 or 20 minutes. Anybody know the total amount of energy in any unit you want? We generally do it in tons of TNT. I don't know why. In EV, ergs, joules. 30 ergs. Yeah, so it can, there's huge range of flaring, but you can have huge amounts of, many megatons of energy released over a very short period of time. And so that was always the trick. Where do I get that energy, and then how do I convert it on those timescales that matter, those really quick ones, on the substorm timescale, on the geomagnetic storm timescale. And so when you look at the equation of motion, you're going to have in the diffusion equation, your dB/dt term. You're going to have a couple of terms, sort of a dynamo term, a motion term, and then you're going to have this diffusion term. So I need to get some way to diffuse that B to go to 0 really quickly. And so when you start looking at those scales, that's where the interesting physics happens. And so the current state of the art in reconnection physics is trying to develop a cross-scale global model. So how do I make a magnetospheric model, which are MHD right now? We could add Hall physics and all different types of physics in it, but we can't get the physics of the reconnection region. So the only way we can do that is looking at the kinetic region. So a lot of effort is going on now is to try to couple particle models with global MHD models. And so you have to pass the information back and forth between your PIC grid, your particle and cell grid, with your MHD grid. And how do you convert an MHD parameter into a kinetic parameter and vice versa? And And so some of the early processes are going on now, and we're hoping that MMS and all of the instruments are pretty much turned on. The only anomaly that I know of for the magnetometer is one boom went out, I think 97% of the way, which doesn't really matter. But everything looks good. We're hoping to get a series of papers out later this year, flying through some of these diffusion regions. Okay, so for this afternoon since lunch, there's a lot of different ways of organizing conceptually this broad field of heliophysics. We can do it by domain. I'm an astrophysicist. I'm a stellar astrophysicist. I'm a solar astrophysicist. I'm a heliophysicist. We can all divide them up. One way is to think about in a fluid picture, in a magnetic centric picture, an ideal MHD picture, and think about that the structures that we see can be reduced to three different things. We have cavities, current sheets, and flux tubes. And so if I'm going to be interested in the change and flow of mass, momentum, and energy, those are the three things I'm going to look for, crossing those current sheets or those cavities boundaries. Reconnection is this cross-scale phenomena that the global scale, how much energy I'm dumping into the system, determines the microphysics of the reconnection region in the magnetotail. So I have this delay from the day side to the night side. I have intrinsic instabilities that can go on, as well as these external drivers. But this momentum, mass, and energy transfer happens over a broad range of scales. And the same physics is used to explain a broad range of rapid energy release. If you have a big DEDT, an explosion somewhere, I can call it a substorm, a storm, a flare, a nanoflare, a coronal mass ejection. Much of the physics is thought to be the same. So if we really want to understand heliophysics, magnetic reconnection is that mechanism, is that process that connects those three different domains, one cavity to another, across current sheets, and allows flux tubes to interact. And the reason why you'll be studying reconnection, if you're into that, is this cross-scale coupling forces all of us that were trained as kineticists and MHD people to work close together, and we normally don't do that. And so we need to learn each other's language and be able to take each other's tools, an MHD tool to recognize the entire global structure with the particle that will determine the diffusion region. Ideally, Moore's law will continue, and people have done estimates. When can we make a full global particle, full particle kinetic code? It's not that many decades off, but we're not there yet. And so we continue need to make approximations to couple those. So thanks.